All right, so let's see the new uh, material in Unit 6. It's about vectors, and we're going to apply vectors in physics, and also we're going to learn the operations among vectors, like inner product and uh, inner product, or like the other name for inner product is dot product. Yeah. Yeah, I don't know if you heard of it. So vectors, it have um, mainly it has two um, like important concept. Like one is yeah, I guess one, you need a direction. So in physics, like the direction of a force, and then the other is a magnitude. So like, so if in physics, for example, um, or like like, yeah, like which direction does this force go. So for example, let's say the gravity. Okay, so gravity always points down, and then so you can in math you can represent it as a vector which has the direction going down, and also how much force you are applying to this object, or how much gravity, right? So you have the magnitude, um, let's say F, all right, and the magnitude would be mg, right? Yeah. So so here it has like scalars. These are just you can skip this, like scalars, blah blah blah, and then vectors. Yeah. So here's the definition. Vectors, it mainly has described by a magnitude and the direction. Okay, so it's an object that has like two of these important information. Okay, and let's see. Yeah, here are some of the examples that we're probably going to uh, learn using the vector. Like one of them is force, um, and I think, okay, position can also, position vector, that can also happen. Like if we have origin, um, and if I have like the current position is at P, and then yeah, we can definitely use vector to describe position. And yeah, I think mainly the position and the force. Okay, um, but let's see for B, geometric and algebraic vectors. So geometric vectors are um, so if we're in the space, we have two random points A and B, and then we can define vector, you know, as the sign language, math language suggests, like starting point A, ending point B, and then you have a direction. This arrow is like direction, right? Directed from A to B, and then this is a uh, like directed line segment called vector AB, right? Um, yeah, I guess then uh, this vector can be, so these are saying like vector can be defined by 2 points. And then on the right, C is saying like a vector can also be defined using a coordinate system. But I think we have learned it like somewhere before, right? So vectors can be defined by 2 point, and here vectors can be defined by a coordinate system. Yeah, so for example, and then if to represent a vector, I think is that previously it also, uh, interchange like frequently. So if you have a o at the origin, and then a is a point maybe 2 0, so we can either describe this vector v. Sorry, my writing is a little bit sketchy, but so there's two ways that we can write this vector v. We can either write it v as o starting from o to a, right? So OA is not equal to AO, right? So I think we talk about it, right? The direction of the vector starting point and ending point is quite important. And then we can also very conveniently just describe this vector using this coordinate. This is actually the coordinate of point A minus the coordinate of point O, okay? So A is 2, and then 2 minus 0, and then 0 minus 0, right? So this is quite important. And so even here, algebraic vectors, so even the example it gave is just a coordinate, but however, this should be, vectors, there should be a starting point. So this should be equal to some AB, right? And starting point is A, and then the ending point is B. So similarly, as this coordinate is representing, this should be the coordinate of B minus the coordinates of A, right? So it's not just a point, okay? Yeah, so I can definitely, maybe change it a little bit. Maybe let the origin be here, and then this is my A, and then this is my C. So A is at, all right, number 5 0, and then C is at 2 0, okay, 2 0. And then what about CA? C to A, as you know, so it should be like 5. It's not CA is not 5 0 anymore, right? It's not simply 5 0. It is 5 minus 2 and 0 minus 0, okay? And then position vector. Position vector is the directed line segment OP from the origin of the coordinate system O to a generic point. Yeah. So for any point in the space, right? So this is a convenient. So A, B, C, D. These are just words like language describing the concept, right? So, but in higher level overview, you just need to keep in mind vector has two components for information. One is direction, the other is magnitude. You just need to keep it in mind, okay? And then to represent a vector, because we talk about a lot of words, right? But to simplify it, it's just one using vector starting point, ending point. So we have an arrow. This arrow means direction, right? This arrow means direction, and then the magnitude will just be coordinate B minus coordinate A, right? And then a coordinate system, okay? And this is actually for any generic P. If the P coordinate is x, y, z, or just x, y, and because the origin is always 0, 0, right? So the p, so OP, this vector is actually the difference. It's still the difference between coordinate p and the origin. So x minus 0, y minus 0. Yeah, and it happened to be xy, which is the coordinate of p. Okay. Yeah. All right. Yeah, but these two, either write an AB or coordinate system, these are essentially the same. Okay, essentially the same. Yeah, we just have a higher level overview. Like, although we use different words to describe vector, but like in the end, it's essentially the same, just direction, magnitude, and even we wrote it in coordinate system, but it's essentially the the, the same. Okay, and displacement vector, okay, directly line segment from point A to point B is still something that we talked about before. Okay, um, essentially the same concept. Example 2, so draw the position vectors OA, OB, OC. Alright, yeah, I think we did something similar before. OA, like this, right? Starting point. So starting from O and then to B, any point B, okay? And then starting from C, okay, starting from O to C. Yeah, is nothing too complicated. And then displacement and displacement, but these are essentially the same, right? The starting point, ending point. So because these A, B, C, it happened just because the starting point is origin, so the vector happened to be like the same as the coordinates of A, B, C. Okay, but it's really okay. So P, Q, and R. Yeah, I don't know why am I drawing this. I think you guys know. Um, yeah, Pythagoras theorem, we're also using it a lot, right? Yeah, so just side square is a squared plus b squared, and then we'll just see later how it's going to be applied. A magnitude is the length, size, norm, or intensity of the vector. Magnitude is this. Okay, yeah, magnitude is just the norm. So this is a norm operator. Okay, norm or length operator. Yeah, remember we when we were in class, you remember that we did something together, right? I think, yeah, I think that's our class that we were calculating a length together, right? So if you remember that, um, so for example, if um, let's see, e.g., so if v is, say, uh, x, yeah, sure, xyz, all right, and then what is, so this operator just mean if we have any entity, I'm just going to have like a dot here, any entities object in here is going to do this norm or length transformation. Okay, so the norm of v would be just, yeah, but this is the Euclidean in Euclidean space in order to be rigorous, but I think it's fine because in high school we're just gonna assume that it's Euclidean. Yeah, Euclidean space, like you can simply think of like R2, R3, or Rn. So this would be like the square root of, because this is not norm square, okay, so just the norm is gonna be square root s squared plus y squared plus z squared. But however, like if you so for example, we just learned the Pythagorean theorem, right? Pythagorean theorem, so c squared is going to a squared plus b squared. So if we are going to be two dimension first, two dimension, s y, and then this is just square root of x squared plus y squared, right? And then this is just simply Pythagorean theorem, right? So if you that's what I mean in math. We don't remember everything, but to understand, right? Because if you understand, it's very natural. So if we have a point, its coordinate is xy, and then on the x-axis this is length x, and then on the y-axis this is length y. Okay, yeah, so this is length y. And then what about the vector length here? Okay, the vector, so this like chocolate color, this is the length of v, right? So that's where we are calculating. And so for note that v, so norm square is just x squared plus y squared, right? So this just feels so natural to you, isn't it? Isn't it feel very natural to you? And then notice that this is a norm square, okay? Square. And then this is simply actually just this norm square or length. So norm is there's another name for this. This norm square formula. It just our Pythagorean theorem. Okay. Okay, let me see the spelling. Pythagorean. Yeah, okay. Pythagorean. Yeah, something like this. Alright? Yeah. So this norm formula, it should be quite familiar to you. Alright? Because this feels natural, isn't it? Like the v vector length, it just its coordinate sum of square, right? It's actually just Pythagorean. That's something that we all know for a while, maybe heard of. And also in higher dimension, if we're going to generalize it like 3D, okay, we have little space here. So this going to be v is going to square root of x. Okay, sorry. If we have v is x y z in 3D, right? So this will be x squared plus y squared plus z squared. Alright, it's not bad. And consider the following diagram. Let's find the magnitude of OA. Okay, OA. Yeah. AB. Okay, AB is here, and then but first let's just see OA. We can first just write out in the coordinate system just the coordinate a minus the coordinate of 0, right? So we can say like minus 2 and 2 minus 0, 0. Okay, so yeah, of course you find out because it's starting from the origin, then it's just going to be like 2, 2. Yeah, you double check with my answer, right? Because I could make a mistake. And then the magnitude, I think it's just applying our formula, right? Yeah, just square root. You definitely have this square root, right? It's super important because if you don't have the square root, then you'll be having norm square. Okay, definitely keep this in mind. Don't make a mistake, right? Everything that that we go through, spend the time already in class, make a remark. I hope you don't make a mistake later, right? That's why we are even spending this time. Okay, so square root of 4 plus 4, and then square root of 8, and then 2 square root of 2. Okay, and then AB. Yeah, what about AB? You can directly okay. Well, from the picture you can see either like square root say 1 square, because this side is 3, this side is 1, so you can say square root of 1 square plus 3 square is, what is this? Since 3 square is 9, so 1 plus 9 square root of 10. Yeah, you can do this, and you can also, the standard way is so first we want to know how to write this vector AB, right? We want to know how to write this vector AB, because B is going to be B core. So AB vector pointed to B, right? So B is our ending point. And so we're going to use the coordinate of B minus the coordinate of A. Okay? Yeah. The coordinate of B would just be -1 and -1, okay? And then the coordinate of A would be -2 and 2, right? Yeah. Yeah, so you make sure that AB, you use B, the ending point, minus the starting point, okay? Yeah, so yeah, I point this out, so don't make a mistake here, right? Just as an example, OA, you know that is the A is of course the A coordinate minus the 0, 0, right? So from this example, you know that it's an ending point, ending point. This is A, right? This is point A, and then minus the point O. So from this first example, you know the order, which is like who minus who, which minus which. All right, and this is going to be -1 plus 2 is, yeah, and 1 plus 2 is 3. Yeah, and this is negative, wait, oh, sorry, this is 1, and this is -3, okay? Yeah, so it's the same magnitude that we are going to calculate. And then BC, I think I can leave one of these exercise in the exam, right? Yeah. Okay, 3D, Pythagoras theorem. Yeah, here, so AG, if we are going to connect these two, right? So it's cross the diagonal of this like 3D cube. Yeah, so it's going to be like the A squared plus B squared plus C squared, okay? And of course, yeah, it's not easy to draw it, right? Yeah, so it's not easy to draw this 3 coordinate. Okay. yeah, and then AG, just like we mentioned, right? Here, the example, XYZ 3 coordinate. So AG, the norm of AG, what is the norm of AG? Norm without the square is still going to be the length, right? So this is going to be the square root of a squared plus b squared plus c squared, okay? Yeah. And consider the side lengths equal to 10. Magnitude of these following vectors. Yeah, this is just the magnitude of the vector is just our side length, okay? It's just length. And then you see that because it's saying the cube, okay, so I'm just gonna assume these are right triangle, and then BD, you can draw the like the bottom side. So BD, yeah, I think you might know. So this is 10, this is 10, and then asking the BD magnitude is still doing the yeah, this is actually just a formula for calculating vector length, right? So this is formula, not just a Pythagorean theorem. Okay, so this formula is just 10 square plus 10 square. Okay, and BH, yeah, so BH is again, I think you know, right? I can ask you in your maybe pick one and ask your in your exam next weekend. Don't be too nervous, it won't be hard, right? It's just something that we went through. Everything shouldn't be hard. So this would just be the BH would be square root of, this square, BF squared, so 10 squared plus BA squared, 10 squared, and then BC squared, 10 squared, right? So I already told you. Okay, BH. Alright, so maybe I can pick one of them in the exam. Okay. But again, but again, I already told you, right? Yeah. So it shouldn't be hard. Consider the regular hexagon ABCD. Okay. Alright, so find the magnitude of the following vectors. Yeah, what about this one? Okay. Okay, so this one, you should first think on your own a little bit, right? Okay, so with side length equal to 2, this is direct. So AB is the side, so this will be 2. What about AC? Okay, I didn't read this question in advance, so I also need to think about it. Right, and then only know we have a hexagon 6 side, right? So something about the angle, some information about the angle, right? So now you should process this information. Okay, so I read the first sentence is hexagon, 6 sides, and then what about the angles between these? Because for example, if I'm, and also it's asking AD. Okay, I'm just gonna draw connect AD. Yeah. Okay, so if I'm going to know AC, but it's good that I already know BC. it's like like a triangle with two sides that's equal, right? Um, right? And yeah, then usually if we know these one of these angle, and then we can know uh the length of this part and then the other half, right? Yeah, that's how we approach things, okay? um right, like how would you usually compute um the other side of triangle? You would do, like, would you do something similar as this? All right. And another actually, because this is hexagon, so we have, if we gonna connect these if we're gonna connect these lines, uh yeah, diagonals, if I'm connecting all of the diagonals, as we know, the side lengths are all 2, so 2, 2, 2, 2. Yeah, so the sides are all the same. And also, let me see. And also, I think that this is a regular hexagon, meaning, yeah, regular just means the side, like, however I connecting these diagonals should be similar. should be the same. Right, the length of the diagonal should be the same. Yeah, so what does it further imply? This would further imply that these angles are the same. Okay, right? Because it's a regular hexagon, so this would be like 60 degrees. Yeah. And then what does it say about this angle here? You should guess a little bit, or help me guess, right? So if these are all 60, 60, 60, yeah, then what does it say about this angle? Okay, yeah, you can think about it and deduce, right? So I'm just gonna stop this video and upload, and then you can also think about it a little bit.